So, welcome to the first session this afternoon. We have two speakers who are going to talk about challenges in energy management and weather forecasting. So, our first speaker is Yannig Goude from EDF France, and he's going to talk about future challenges in data analytics for energy management.
Thank you very much. Could you hear me well? Is it okay? Yeah. Okay. So first of all, thank you very much for the invitation. I'm glad to be here in this very nice building, and it's always a pleasure to talk in front of such an audience. I'll try to give you an overview of the future challenges in data analytics for energy management. To be honest, I'm more a specialist in data analytics for energy markets. But recently, I had a few exchanges with other colleagues at EDF R&D on other data science topic. I will give you some insights on that. So it is a joint presentation with Georges Ebraille from also EDF Lab, and I will talk about the topics which are in blue in this summary. So there is many data science application at EDF, from power generation, like process monitoring and predictive maintenance for power stations. We have, I will show you, we have a lot of sensors that measure information for a lot of years. So we have many data to analyze and use to improve our power generation process. We have also a hot topic, which is power generation for forecasting for renewables. I will talk more deeply of energy management, load forecasting, balancing and optimization of generation and consumption. For example, demand response management problems. We have also a lot of work to do with electrical networks, smart grid operation and maintenance of these networks. I won't go into this point because I work in this area only for the load forecasting problem, so it will be related to the load forecasting. And then another big topic is the commercial part of energy management, like customers and sales, how we can use new data, new smart buildings, smart homes, smart grids to propose new services, to propose energy diagnostics, those kind of things. So I don't know if you know this object. It's a smart meter in France. So it's a big amount of data which are coming, because in 2021 we will have all these smart meters deployed in France. So we work also on how we can use this data for better forecasting and better management of energy. So about power generation. One hot topic at EDF is how we can store and analyze big data from operation and maintenance of the nuclear power plants. What is interesting is that we have a lot of nuclear power plants, and we have high volume data which are quite clean, in the sense that everything was thought to be similar in the different nuclear plants in terms of data architecture. So this is stored up to 40, 60 years, and this is high frequency data, and we have about something like 10,000 sensors per plant. So it's I think a nice playground for statisticians. But there is also problems coming with this data. So mostly it's time series, but there is also text information, like maintenance reports. This this text is a non-natural language, so we have to specialize our analytics on this data. We have image, we have sound, we have documents like a lot of reports written by different engineers. So the first step was at EDF to make this data accessible for every data scientist in the EDF group. So we have conducted different comparison of big data storage solution, and finally we arrived to a Hadoop cluster, a data lake, which is an Hadoop cluster where all these historian data are stored and could be easily accessed in real time. So it's I think it's a very exciting moment at EDF, because now we can work and produce real-time data analytics. So as I said, there is a different data science problems coming with that. It's not an exhaustive list, I think, but it's a good beginning. So we have to build a lot of we have to do a lot of studies to make a link between physical models and machine learning methods. Typically, what arrive at EDF R&D is some engineer are coming to us saying, okay, I have my physical model that is able to detect a break in a sensor, something is going wrong. I have different feature I know that I need to look at. Could you improve this physical model with machine learning methods, or could you do it automatically? Those kind of consideration. It opens the way to data augmentation, transfer learning. Okay, I do a model on a small machine, which is a physical simulation of a real machine on a plant. Could you build a machine learning model that will work on the real nuclear plant? How to conciliate complex heterogeneous data, as I said, text, sound, image, and time series together. Time series at various resolutions. So we have a sensor. Sensor could be at different resolution, but we have also punctual measurements. Sometimes there is an engineer coming to the machine, open it, and doing some specific measurement, more precise than the information you can have from a sensor, but it's only every 6 months or every year. So how you conciliate sensor data and this kind of data. There is also the problem of data visualization. Data visualization for different end users. It could be my boss, it could be another engineer, it could be another data scientist. So we have to build different tools for these different topics. Change point break detection. It is interesting because related with this morning talk, because we have different sensors, and the problem is that is there a change in the behavior of a machine? Is there something that is the beginning of an alert? Those kind of consideration. And then, but not the least point, how we can certify, validate, and interpret machine learning models. It is something very sensitive when you work on a nuclear power point, and but also in energy management. How you can convince people that your model will always stay in the validate space for decision. I think it's a big question we should all consider. So another big field, so I will maybe more enter into the detail of the method here, is energy management. So here it's an example of a data set, a US data set where you see the relationship between consumption and the temperature in the US. So it's in New York. You see that there is a big increase of the consumption when the temperature is high due to cooling consideration. So it's an example of a simple model you can build from real data to forecast consumption. We have to do that for at a national level, the demand forecasting to optimize the production units. But what is really challenging now is that it's becoming so energy world is becoming more and more local. There is more people that who produce their own electricity in their house. There is new smart grids that allows people to optimize locally consumption and production on the network. So we now have to forecast not only one point per country, but all the substation, for example, of the distribution grid in a country. So it's going from one model to something like 2,000 models in France, or even 20,000 models if we go deeper into the grid. So we have to produce machine learning methods which work automatically. Another question, when you want to forecast electricity consumption at a local level, is how we consider the new information from meter data. So here is some graphs to show you the nature of smart meter individual consumption given by smart meters. So here you see it's from a data set, a public data set from meter experience in Ireland. So we have access to something like 2,000 residential consumption during 1 year. So here it's one people during 1 year at a half-hourly resolution. Here it's 1 week, and you have 3 different people here. And what is you clearly see that it is probably quite difficult to forecast the consumption of one people. It's difficult to know when he will be in holidays, when he will put on event or something like that. So a difficult task. But if you look at what's happening if you aggregate people together, then it's becoming easier. It's the law of a large number, in fact. So you here on this graph you see I took randomly among the 2,000 population 10 people and do an aggregation, and here it's a half-hourly it's a 1 day of consumption at an half-hourly resolution, and in gray you have all this subsample of 10 people, and in black you have the mean of all this subsample, and I do that for 50 people, 100 and 200, and you see clearly that the variance of the signal is becoming lower, and it's more forecastable. Another industrial motivation of new machine learning for energy markets is probabilistic forecast. Why? Because we are living in an energy world which is more and more random due to random generation induced by renewable. So here it's from the national grid data in the UK. You have the wind power production and the solar power production in the UK, which clearly increased during the last years. And if you represent the daily photovoltaic production in the UK, it looks like that. So it's a curve which has a maximum during the afternoon, but it could be very random along the different days, and it's more the case for the wind power. Another goal of our work at EDF is online learning for energy markets. So I'm sorry because I didn't put for confidentiality reasons. I won't say you what are these covariates, but the main idea is that we have to forecast in real time signal like the difference between consumption and production for traders, because if you know in a few hours what will be the value of this signal, then you can trade on the energy market. But roughly, what is interesting in terms of machine learning is that we have a lot of data, but the time series are really unstationary. So you need to track signal and build very adaptive models. Another topic is demand response, and it is also related to smart meters, because smart meters are a way to communicate in two directions with individual customers. You can have his consumption, but also you can send information like a tariff option or any incentive to consume or not. So we work on that also to design algorithms similar to in the spirit of what was presented this morning in the casino. You have a game which is how to optimize a park of consumer, and you have to know what kind of signal you send to everybody in real time. So what kind of tools we use? We have we have worked a lot on generalized additive models of this form. So consider here you have the consumption, and you decompose it into additive effect depending on temperature, the hour of day, the day in the year you are, plus a noise. And this model classically use spline basis to estimate this nonlinear function. And what is interesting for us is that it's a good trade-off between interpretability of the model, because it's additive, so you can separate the effect of each covariate, but also it's very adaptive in a non-parametric way to the data. So here the graph represents different spline bases, and if you fit that on a real data set, so I don't know if you see the gray point here, this is consumption in function of temperature, center, and you see that if you fit a spline, you obtain these black lines, and depending on the spline basis, you have different effects, so you have to choose the good spline basis decomposition. And for that you minimize such a criteria, which is a mean square error plus a penalty for favorizing a smooth function. So we did that on substation in France. So all these red points, the time series looks like that, so very different. And using GAM models, you can fit a model automatically on all those substations, and it is used in operation by the distribution grid. We tried also to add one step of automatization, because in the GAM models here, you have to know in advance what will be the covariates here, and you can think about like for lasso regression about finding automatically what is the best subset of covariate among a big set of covariates. And it makes sense because probably you don't need the same covariate in the south of France and in the north or in Brittany. So we design a L1 penalty algorithm to find automatically this best subset. And our experiments show that we were able to recover, as well as an EDF expert, the good covariates for forecasting. Also, we develop quantile forecast, quantile GAM models. So the idea is that instead of minimizing a square loss, you minimizing what we call the pinball loss, which is well known in a quantile regression. And then you can estimate one GAM model per quantile of your consumption. So typically you have one effect per quantile. Here it's a simulation example, and we use that for forecasting probabilistically the load locally or nationally. I'm sorry, maybe I have to go quick on that. But we compare our solution, so it's a joint work with Matteo Faziolo and Simon Wood from Bristol. We compare our algorithm on two data sets, one from a competition on a US data set that was done in 2014, and one from the UK grid. And you see here, so in black is the loss, in terms of pinball loss we have observed using Gaussian model, and the loss we observed with our solution on a variant we have implemented in blue on red. So it is uniformly better than the Gaussian, and then a boosting method on all the quantile on the JEFCOM and UK grid. And here you have the different function you obtain for different quantiles on these data sets. We have also another variant, which is so if you remember well the individual data we represented before, there is some peaks in the data which are badly estimated with spline models. So the idea here is to have adaptive models with some part which is estimated on a spline basis and some part estimated on a wavelet basis. So wavelets look like that, and they have this nice property to be able to estimate peaks on the data. So it's interesting, for example, to recover tariff effects or anything that looks like peaks in load consumption data. So here it's an example of simulated data set. So with such a model, suppose you have 8 covariates, and you have the transfer function between x and y are like the red points. This kind of model is able to recover such a structure. So a smooth effect coming together with unsmooth effect. The only drawback of our approach is that for now we need to know in advance what will be the smooth and the unsmooth effect. So we are currently working on automatizing this. It's an example of a real data set. So here you see or not, I don't know, that in red you have the spline estimation. In blue and green, which is two variants of wavelet-based estimation, which recover better the peaks. So another topic is how you use individual meters to improve the forecast of the total of a population, because energy markets are organized in such a way that you are paid according to the total consumption of your portfolio of customers. So it's the objective. I have different individual curves, and I want to forecast the total. So the idea is I can build clusters of people, do a model in each cluster, and then aggregate things. So it's a joint work with Ray Rocuglieri from Lyon and Jean-Michel Poggi from Paris Sud, Benjamin Oder from Paris Sud University. What we did is that we, as in a different previous publication, we try to build cluster according to a forecasting goal. We tested that on a set of individual customer, big industrial customer from EDF. And roughly the idea is that we compress information from this 20,000 customer, measure on 1 year of data at half hourly resolution. We compress it using wavelet decomposition to a small matrix. Then we do clustering, and in 2 steps. One step, which is quite greedy, obtains super customers And then one step which is more precise to build clusters. And what we obtain is that here you have the forecasting performance you obtain using only the past of the total of, so only one cluster in fact. And here if you build cluster, here you have the number of clusters we built. You see clearly that you improve the forecast performances from 2.15 to 1.80, which I don't, yeah, it doesn't look maybe too much in terms of improvement, but in terms of energy management, it can cost a lot to lose 0.5% of forecast error. So here you see the different cluster we obtain. So here you have the weekly profile of the cluster. Some are really dependent, some are a high variation between night and day, some not. The peaks are not at the same place, and there is no the same, they don't have the same behavior between weeks and weekends. And during the year, there is some with holidays, some with no holidays, etc. Some are higher during holidays. It corresponds to touristic areas, for example. Okay. Another topic is automatic calibration of machine learning algorithm. So here we don't do so much, but what I want to point is that if you look at solution current software which do that, you can see they have a big popularity in the machine learning communities. For example, I don't know if you know Caret. Who know the Caret package in R? It is a package that allows you to automatically fit machine learning models with an automatic grid search and cross-validation techniques, for example. And if you look at the number of downloads during last year of this package, there is a big increase. And we use it a lot of times at EDF when we have a new data set. But what we saw is that there is a potentiality to improve this grid search in terms of forecasting of time series. So we have a current work on that. And finally, I don't know if I have some 1 minute only. Okay, so I will go very quick. We have work on expert aggregation. So it's a topic of related to online learning. So we have a data set, a stream data set, and we suppose we have access to, we want to forecast it. We have access to different experts that produce a forecast of this stream, and we want to aggregate them in real time. So it's I think interesting because it is often the case in the industry that you come to a subject and you have different experts producing a forecast, and you want to optimize that. So I go quickly. So we have work on exponential expert aggregation on individual seconds. If you are interested, we can talk later on that. And there is a nice book on these methods. And we have a R package. You can test it. It is on the CRAN, so you can download and test it on real data. And we are happy to have feedbacks. And if you want also, I have some time after the talk to do a demo. Just ask me. What is interesting is that we are able to. So in this example, you show we have to forecast the national consumption in France, and we have three different experts. And we propose an algorithm that automatically combine this expert and obtain a performances which is very close to what would be the best expert, the best convex aggregation that could be calculated afterward. So to conclude, so we have different perspectives. I didn't talk today, which is of course, deep learning. I have to work on deep learning because everybody in my company talked to me about that, so we do it. But to be honest, it works for forecasting. I have also some ongoing work on random forest on time-dependent data. So random forest is a very nice algorithm to explore new problems automatically, and we use it for forecasting. Bandit algorithm for optimizing a demand response. So in the sense to find automatically the incentive to send to customers. We have a PhD on that with INRIA and Paris Sud, and we have some work on hierarchical models. So the idea is how we can use spatial information or information on at different scale of the grid to forecast one point of the grid, and also with deep learning. And the last point is if you are interested in testing your statistical algorithm for forecasting of load forecasting or production forecasting, I have listed some open data sets that you can access, and I would be happy to see publication on these data sets for my work. Thank you. Yes?
When you've done the clustering and it leveled off at around about 10 clusters, do you
Yeah.
have a rationale or explanation as to why it settled on 10? Is there an underlying physical reason?
So what is interesting is that this number of 10 is close to the number of profile commercial people use for operation. So it's I don't know if so probably it's physically explainable behind, because we have also so I didn't talk about this work, but we did something using matrix completion techniques to compress information on an individual data set, and we saw that it is quite sparse, in fact, a matrix of consumption, and the real dimension behind our individual consumption is more or less 10, in fact. So it's, we are not so different in terms of consumption.
So let's thank Yannig again.
Thank you.